Okay, another training session for electric drives, chapter 4. Let's get started. Okay, so now we have variable speed DC drives, variable speed DC drives, right? And when we're studying in the past, we just said, oh, you can use solid state control involving power electronics, and then we'll look at that one. So this is where variable speed DC drives make use of the solid state control method. So we'll look at how we can use them to achieve what we want to achieve. Okay, okay, let's see. So just take time to read all this part. Okay, this graph is not any complex graph. You see, we have the motor. The armature current is constant. It's almost constant, right? It's constant. This armature current here. You have the armature current here. Now, in this phase region here, we are varying the voltage. We say that when you're varying the voltage, what do you do? When you're varying the voltage, we say keep the flux constant, right? So if IA is constant, and you are keeping the flux to constant, then it means that you have a constant torque. Because these two are constant. That's why this region is called the constant torque region. So constant torque region, you keep 5 constants, then you vary voltage. This is the voltage here. You vary the voltage. For that reason, the torque also becomes constant. Okay. But for the field weakening region, once you start reducing the field, what happens? The torque comes down. When you start reducing the field, the torque comes down. So the torque comes down here. The torque comes down here at a constant I. And in this region, you keep V constant. As you vary phi, you keep V constant. So that's what this graph just means. Then the constant torque region does not mean that the motor operates with constant torque all the time. But it means that if you want a constant torque, you can have a constant torque. So that's what it is. The term constant torque does not mean that the motor will produce constant torque, but rather it signifies that the motor can produce constant torque if required. Okay, so take note of that too. Take note of that. Okay, so that was that was 4-3. Okay. Now, as I said, let's just move on. So take the time to read all this part. Okay. So we know that was for the quadrantal diagram. This was speed against torque, right? Yeah. Over here, speed and torque are positive. Here, speed is positive, torque is negative. Here, speed is negative, torque is negative, and here is negative, but torque is positive. So realize that if I want, assuming the motor is operating on these characteristics, right? If I want the motor to operate in the second quadrant, how do I do? I have to reverse the current. Because negative torque, if I have torque is equal to K phi IA, negative torque implies current is negative. So once I'm able to come to the second quadrant where torque is negative, means that I have to give it a negative current. Okay. If I want a 4 quadrant operation, I should be able to reverse the EMF too. When E is equal to what? E is K phi omega. If I reverse the speed, if I make the speed negative, my E will become negative. So once I'm able to make the E negative, it can operate in quadrants 3 and 4. For a 4 quadrant operation, actually, that's what the statement means, that for a 4 quadrant operation, the converter should allow its output voltage and current to reverse. You get it? Yeah. So that's it. Now, We'll take the control circuit one by one. So first we'll take rectifier controlled, right? Rectifier controlled. Then we'll see all the types under rectifier control. Then we'll take chopper, DC chopper circuits. Then we'll see the types under it. That just brings us to the end of controlling speed of the DC drive. Okay. Alright. So now let's see. Let's take the rectifier controlled speed drive. Control rectifier drive types. So the first type we'll look at is the single phase. So over here it's not difficult. What you must know is that you must know how the circuit is run and the formula. That's all we are doing. Because I'm just saying that if you have a motor like this, right? If you have a motor like this, right? And I want to vary, say, the voltage of this armature here. I want to look at connect a rectifier here, right? Because you know that with rectifiers, you can vary the output voltage of the rectifier. You can vary the output voltage of the rectifier by varying the what? By varying the firing angle. So if I have some voltage supply here, Vs, AC supply Vs, right? You go through the rectifier. The rectifier gives me a certain output DC voltage. Then that DC voltage output becomes the input to the motor here. So as I'm able to vary the angle, the firing angle of this rectifier here, I can vary the output voltage. And once I can vary the output voltage, I should be able to vary the speed of the motor. I should be able to vary the speed of the motor. Okay, so that's what we're going to look at. So we're looking at types of this rectifier that we can use. The first one is single phase semi-controlled. It's not fully controlled, semi-controlled. Semi-controlled means that not all the diodes are fired. Not all diodes are fired. Single phase semi-controlled rectifier type. So let's see how that one is. So we read all these parts. So that one, this is the formula for it. So if I input a certain voltage, let's say 240 volts here. If I input 240 volts here, the output voltage, I'll have a certain value, right? And by varying the firing angle, this alpha here, I can vary the output of the voltage and hence vary the speed. So here you must know the formula. So single phase semi-controlled, the formula is √2 V over pi 1 plus cos alpha. Single phase semi-controlled, the formula is √2 V over pi into bracket 1 plus cos alpha. So we have that. So let's see the diagram for it. And I said semi-controlled because you see, these are the diodes, right? This is fired, but these two are not fired. So that's why it's semi-controlled. So you can just tell that it means if I fire these two, then I'll get what? I'll get fully controlled. That's all there is to add. That's all. Fully controlled. So that's it. But this is semi. So without it, it is semi-controlled. Single phase semi-controlled rectifier. So for a single phase semi-controlled rectifier, we have our V out to be what? √2 V over pi 1 plus cos alpha. And you vary alpha, vary the output voltage. Once you vary the output voltage, you can vary the speed. Let me put W here. You can vary the speed. That's it here. That's how the variable speed DC drives operate on single phase semi-controlled rectifier. Now let's look at single phase fully controlled rectifier. When we do fully controlled rectifier, the formula is just times 2. V naught is equal to 2 V over pi cos alpha. There's no 1 plus. This is the formula. So once I vary this, I can vary V out and vary the speed. So it's fully controlled. You can see that fully controlled. These two are also fired. They are all fired. And for the field one, I can use either semi-controlled or fully controlled. It doesn't matter. I can just use any of them for the field. The main one, I'm looking at how to vary the amateur voltage. That's my main focus right now. But it doesn't matter. Okay. Also vary the field winding part. Okay, take your time to read all this part. So the formula is here. This is the fully controlled formula here. So we have single phase semi-control, we have single phase fully controlled. Now we have single phase dual converter. Dual converter. So you can see that one dual means what? Two, right? So now you have two separate sets of rectifiers connected to the armature of the motor. Are you following? So you have one set. So let's see. Yeah. So just read all these parts. Okay, so let's take a question. Example 6. A DC separately excited motor has constant torque of 60 Newton meter. The motor is driven by a fully controlled converter connected to a single phase. So this is the supply voltage. This is the VS, the V in the formula. The field constant is 2.5. Okay. Then I have my RA to be 2 ohms. Calculate the triggering angle alpha for the motor at 200 rev per minute. 200. So I'm supposed to calculate the triggering angle. So the formula that has a triggering angle in it is what? Where V naught is equal to V naught is equal to what? 2 root 2 V over pi cos alpha. I know V. I want to find alpha. Let me find V naught or the voltage of the armature. You see, when I drew the diagram here, I have my rectifier here, right? The voltage that comes here is what goes to drive the armature, true or false. So let me find the voltage of the armature. Now, I know that speed is equal to what? VA over K phi minus RATE over K phi squared. I know the speed. I continue to rad per second. I know K phi. I know RA. I know torque. So I can find the voltage of the armature here. And that voltage becomes the voltage here. This V naught here. You get it? You can input V naught here directly. Once I have that V naught here, I can now find cos alpha. So that's what was done. That's what was done here. So from this formula here, you found your V naught using the formula here. So you just substitute. You know the speed, right? 2 pi times 200 over 60. Then you know K phi 2.5 squared, 2 times 60. So you find V naught. Now you have V naught here. Put V naught into the formula here and make cos alpha the subject. So you just find cos inverse of what you are getting. So alpha is 21.7. Alpha is equal to 21.7. So that's it. That's it for that question. Now, example 7 says that the speed of a separately excited DC motor. Am I muted? The speed of a separately excited DC motor is controlled by a single phase fully controlled. Single phase fully controlled bridge rectifier. So fully controlled. The field, so the armature is controlled by the fully controlled. The field is also controlled by a fully controlled rectifier. So let's see how we can try and draw this one here. Let's see. So I have my armature here, right? It's connected to a fully controlled rectifier here. So it's picking some VS here, giving me some V naught here, causing some IA to go through here. This is supposed to be armature, sorry. Armature. Now I also have my field winding here. It's also connected to a fully controlled. So we can also vary the field current, right? Once I vary the field voltage here, so using the same rectifier, fully controlled rectifier here, I can vary the voltage of the field. That will vary the current of the field to control the speed. Okay. So it says that the field circuit is also controlled by a fully controlled converter, and the field current is set to the maximum possible value. So the field current is set IF. So I know that for rectifier V out is equal to 2 root 2 V over pi cos alpha, right? cos alpha. Now, the maximum field current flows when the maximum voltage is supplied. The maximum field current flows when the maximum voltage is applied, and from 2 root 2 V over pi cos alpha, the maximum voltage is when alpha is equal to 0 degrees. That gives us cos 0 to be 1. So you get V0 to be 2 root 2 V over pi. You get V0 to be equal to 2 root 2 V over pi. This is the formula that I'll be using for the rectifier side, because I'm saying that alpha is equal to 0, because they mentioned that the field current is set to maximum. Take note. It's set to the maximum value. So that's the first deduction we can make. Now, the AC supply to the armature and field is 440 volts. So the AC supply here, this VS is 440 volts. So the V in the equations I'll be using is 440. 440. Okay. They gave me RA and RF. They gave me KV. Now let's talk about this. You see, we know that what? We know that T is equal to what? K phi I, right? K phi I. Now, in a question where they don't give you this K phi, but they give you KV. Okay. Now, note K phi is equal to KVIF. K phi is equal to KVIF. This implies that my torque will become what? KVIF IA. KVIF IA. KVIF IA. So you know why I see K phi, I just replace it with KVIF. That's what I wanted you to know. Okay. Now, the armature corresponding load current, they're giving the armature current to be 45 amps. Armature current is 45 amps, IA 45 amps. Meaning that assume the armature current is constant and continuous. That means we can use the formula we've been using. Find what? Okay, they give us if the delay angle of the armature converter is 60 degrees. So this one here, the armature converter alpha is equal to 60 degrees. Alpha is equal to 60 degrees. Determine the torque developed by the motor, and B, the speed in rev per minute. First question is that determine the torque. Determine the torque developed by the motor. I know that my torque is equal to what? K phi IA. I was giving KV, so my torque is equal to, I say it's equal to what? KV IF IA. Just put it inside, that's all. Your KV was 1.4. IF. Okay, we don't know IF now, but I know IA to be 45. But you mentioned that IF was set to maximum. Now, let me find V naught max. V naught max, the voltage supplied to the field winding. That's what 2 V is for 440 over pi. Because once I know V naught and RF, I can find my IF, right? So IF will be equal to the V supplied to the field. That's this one here. 2 V over pi, 440 over pi, over RF. I was given RF to be 175. So I'll do that. I'll find my IF to be this VF here over RF 175. So let's do it together. Let's do 2 root 2 times 440 over pi. So that's 396.14 over 175 divided by 175. So my IF is 2.26. Once I know my IF, find my torque. KV was 1.4, IF is 2.26, IA was, I think, 45 amps. That's how I'll compute my torque. Now the B says that find the speed in rev per minute. So it's not really difficult, is it? No. This part is more about the formulas. Understanding how it is going into the circuit. That's it here. How my torque? Now the question is find the speed. The speed is equal to what? V armature voltage over K phi minus RATE over what? K phi squared. But we don't have K5, we have KV. When we say K5 is equal to a KVIF. So we take the K5 out, and I'll put KV here. KVIF, I'll put KVIF here. So now, let me find my armature voltage. It's a rectifier, so V naught is equal to what? 2 root 2 V 440 over pi cos alpha. They give us the alpha to be 60 degrees. I'll find that V naught, which is the armature voltage. So that's what will come here. Once I put that one here, I have my KVIF. I know my area, I know my T, I know everything. So I can find my speed. You see, so it's very it works more with the formulas. It works more with the formulas. So just put in everything, that's all. So V naught will be 198.07. So you put in your 198.07, put in your KV 1.4, IF 2.26, RA, talk, everything, and get the answer. So you put in the values, and you get the answer to be 59.05 rad per second. That's 564 rev per minute. That's 564 rev per minute. This is the last question we'll look at. The last question we will look at here. Now, if the polarity of the motor back EMF in example 7 is reversed by reversing the direction of the field current, so the polarity of the back EMF E is reversed by reversing the direction of the field current, determine the delay angle of the armature circuit converter to maintain the armature current constant at 45 amps. So the back EMF of the motor is reversed, right? So the current has been reversed. So the current is now flowing this way. It's now flowing this way. Are you flowing? Yeah. And the back EMF has been reversed. So it means that like now, for this rectifier here, it has I'm not having a rectifier like this, where I can find the input. I can find the input. So I have to find the output here. Because it's now supplying from the motor. You get it? It's now supplying from the motor here. So I know that for a motor, E is equal to what? V minus IA R A. E is equal to V minus IA R A. Right? So I know that V is equal to what? V is equal to E plus IA R A. E plus IA R A. Now, over here, they say the E is reversed, so I'll put E here, negative E here. Let me see. So I'll put the negative there, right? I'll put the negative there, yes. So that's what was done. This E is in the other, it's on the other side. That's why it's not here. This E is from here, and it's from here. See, back EMF is V naught minus IARA, right? V naught. So that E is the same E you use here. You say it's reversed, so you make it negative. You get it? So you make that E negative here. You find your V naught. Put in that V naught into the formula here, and find your alpha. That's it. Oh, that's it. The polarity of the motor back EMF is reversed by reversing the direction of the field current. Determine the delay angle of the armature circuit to maintain the armature current constant at 45 amps. You get it? Yeah. So we found a new V. V is equal to E plus IARA, but the E is negative. So you made the E negative. And that's how you go about it. Then find the power fed back to the supply. The power fed back to the supply will be armature V naught times the IA. V naught times the IA. So that's how you go about it. So that's it. So that's it for this particular question here. that's it for this particular question here. And I'll end this stream over here too. Now I'm trying to make the stream short so that like watching them does not become boring. Okay. So that's it for this video. Continue on chapter 4, 5 in the next video. Thank you very much.